Right now we're taking a trip back to max-min problems. You may recall when we started these, I believe around March 1st, that period of time, when we didn't get through all the problems that I hoped. I had this grand plan that we were going to do one max-min problem per week until we got through a few more of them. And then we kept running out of time before I ever brought any of these problems back. So in between the time that we finish up with our exponent and log chapter, and between that time and the time we start with trigonometry, that is our next topic, I want to throw in a few more of these max-min problems that we hadn't gotten to. So take a minute to read number one, or I'll read it with you. So we've got residents of an island 4 kilometers from shore want to get power to a power station that is 10 kilometers down the shore. And they must lay wire under the water at some point. It costs $2 per meter to run wire under the water, whereas it costs $1 per meter to run wire on the land. So we want to find the point on the shoreline that minimizes the total cost of the project. So I gave you a website for an interactive diagram. I wasn't able to here, I was not able to pull up the interactive diagram. I was only able to do a screenshot, but here's the screenshot of what you would see, and then you'll be dragging this blue dot to show, you know, whether it's and it's showing the total cost. So you can see that as you change the point on the shoreline that we're going to cross out of the water. So this blue part's the water. Here's our island. Here's our power station down here at 10 on the x-axis. And we need to build from the island to the power station in a way that minimizes cost. So if it were just as cheap to build across water as it is across land, then we would minimize the cost by minimizing the path, right? So if we just drew a straight line, that's supposed to be a straight line. If I just drew a straight line from the island to the power station, that would minimize the distance. And if the costs were the same for building over the water as it is on land, the minimum distance would be the minimum cost. Okay, but that's not true. Building across the water is far more expensive. All right, so then you might wonder, well, then let me get out of the water as fast as I can, right? So to get out of the water at the minimum distance, I'd go straight out these 4 miles. But then look what happens. If I go this way, and then I build across, look how much more distance I've added, right? So even though I got out of the water, the more expensive part of the project, I got out of there at the minimum distance I could, I've added so much more distance, even though it's cheaper along here. That was probably not a more cost-effective way to go. And again, you go ahead and pull that blue dot from here to here, right, and verify that that is not a minimum cost. So the minimum cost is actually going to be, or it will result if I find some point on the shoreline, I'm not sure what it is, but I do want to get out of the water faster. All right, I want to get myself out of the expensive portion of the building, but do that without adding so much extra distance that I lose my ability to be cost effective by getting out of the water faster. All right, so we're going to end up with some sort of path like this where we call this distance here x. X is the distance in, wait, what's my unit? Units are so important. Meters. All right, so I would let x, let me open a text box here. Wait, can I put text? Oh, I can. Okay, so let x equal distance in meters that I cross over shoreline. Okay, so then if this is x, think about the whole thing's 10, what would be the remaining distance then? Okay, so think about what that would have to be. And that's going to end up, and actually just to make I have this not set at all on a cost-effective path, but just so that I'm labeling, my actual answer for X is going to be down here more, but just so that my labels match what's on this screen, right? X is the distance between like this origin and then where I cross out of the shoreline. Okay, and so then what's the remaining segment? So this is showing an X that's like 6.4, not a good X at all, right? But that's what I've shown on my screen shot here. So if this is X, then the whole thing is 10. This is going to have to be 10 minus X. Okay, so it's twice as expensive. Remember, out in the water, it's $2 per meter to build across the water. All right, when I start to figure in cost, right? But down here on the shore, it's $1, oh, sad dollar sign, per meter to build across this dry land, the brown portion. So anyway, before we try to set up an equation, let's do some prerequisite skills, all right, so that we review the math we need. So right now, pause your video and solve for C. This is a right triangle, Pythagorean theorem, shouldn't be too difficult, but express C in terms of A and B. Okay, so please pause your video and do that. Okay, we all know A squared plus B squared equals C squared. When I want to solve for C, I would take the square root of both sides, and I hope I hammered this to death earlier in the course that I cannot just simplify this to A plus B, right? Because of the plus sign here, right? If I had a times sign here, then sure, the square root of A squared times B squared would just be AB. But I have an addition sign here, so this does not simplify. All right, so this is how I would express C. Now, back in high school, I hope your high school teacher did a good job of helping you understand the distance formula. If I am looking for the distance between these 2 points, right? This is, imagine that this is a line on the coordinate plane. So this is my x sub 1, y sub 1, and this point is my x sub 2, y sub 2 on the coordinate plane. So if I made a right triangle, right, and I wanted to find this distance here in green, the length of this side is the distance between the x coordinates, all right? The length of this side is the distance between the y coordinates. So based on what we just learned here, the hypotenuse is equal to the square root of the sum of the legs squared. Okay, well, the distance there in green, that hypotenuse is, well, what's the sum of the legs squared, right? That leg squared, oh, I better go to a text box. No, because I can't write x sub 2. I don't know how to do subscripts. So you're just going to have to tolerate my little scribbles here. X sub 2 minus x sub 1 squared. That's not so bad. Plus, right, y sub 2 minus y sub 1 squared. So I hope your high school teachers explained this to you. If your high school teacher didn't, I hope that this helps you get an appreciation that all of those formulas that you've ever learned really do have a meaningful and understandable illustration behind that formula. So anyway, back to setting up an equation here. Okay, so first of all, let's write the distance of this line segment. Okay, the distance here is 10 minus x. The distance of this line segment, all right, so this is the hypotenuse of this right triangle. Okay, so take a minute and express, this is 4, right, on this side. So express that hypotenuse. So pause the video and write a expression for the hypotenuse. The hypotenuse is the sum of the legs, the square root of the sum of the legs squared. Okay, here's the hypotenuse. Now we need an equation for cost. Okay, I want to build this distance here, which is $2 per meter. All right, so I need this distance D, right? So total cost is equal to the cost per meter, right, times the distance, right? That would be my cost. So here's my distance, right, the hypotenuse. So cost, C of X, is equal to 2 times the 16 plus x squared. Then it's only $1 per meter to build the rest of the distance. So there's the cost per meter. The rest of that distance is the 10 minus x, and I want to minimize this. And it's going to be very difficult to answer calculator questions remotely. I hope you got a good handle on how to find minimums on your calculator back when we were on that chapter. Okay, so what I want you to do is graph this. And if you recall, you need to find a good window, right? So what are my possible values of x? What could x be? All right, x can't be negative. I'd be over here. And x can't be greater than 10. I know I'm expecting an x down here. Okay, but I might suggest for a window that we put x between, in our window, set it between 0 and 10, even though we know it's going to be closer to 0. Okay, we do this, we get a zoom fit. Okay, so as I'm sketching what I would get on the screen, please enter that into your calculator and set the window. Okay, so that's what I got on my screen. Most of your calculators, when you go to find the min, you do a second calculate to get the min. Okay, but different calculators have this in different places, but most of you have the 83s and 84s. So you do the second calculate, and that's how you get to the keys where you would select min, and then remember it will say lower bound, so you'll mark here. It'll say upper bound, so you'll mark here. Okay, and then you select, and I don't know why the TA 83s and 84s will often have a place where it says guess. I don't know why they think you want to guess what the min is, but you just hit enter again when it asks you to guess. And you're going to get x equals 2.3. All right, and we want to label that as meters. So 2.3 meters off the shoreline. And then the y coordinate that you get, I already deleted mine, I'm sorry, I don't have it, but it was like 16,000 something. Remember, what is the y coordinate? What did we graph as y? All right, and what we graphed as y was the cost. Okay, so the y coordinate is telling you the minimum cost. So on Wednesday, we've got the quiz on Wednesday, and we'll do another one of these types of problems on Wednesday, do a few more on Friday, and then we will be ready to move on to some trig.